Thank you guys all for coming out tonight. So just a little bit more about my background. I was born and raised in Vancouver, British Columbia. I have an undergraduate degree in geology, and then I did my PhD in planetary sciences, where I mostly focused on Martian materials and remote sensing. And since coming to UCF, I've kind of branched out a bit and have focused more on kind of the practical side of space exploration. So looking at things like asteroid mining and space resources. And what I'm going to talk about today, I'm going to give kind of a broad overview of space resources, why we'd want to use them, what's actually available. And then I'll talk about some of the projects that I'm involved with at UCF to try and make some of this stuff happen. And I think what we'll do is if you have questions, just save them for the end, and then we'll do like a Q&A session at the end. Okay, so I thought I'd start out with just a little bit of trivia. And these objects right here, they don't look like much, but these are beads found in ancient Egypt that are dated to 3200 BC. And these beads are actually made of iron from iron meteorites, okay? So it turns out that humans have kind of been using resources from space in one way or another for more than 5,000 years, okay? Now, this is kind of cheating because, you know, these meteorites fell to the ground and you would just pick them up and use them. So what I'm going to be talking about today is more along the lines of this kind of stuff, right? These kind of science fiction visions of the future where humans are working and living in space and using resources either where they are or transporting them back to Earth or to other places in the solar system. Now, before I get into kind of the nuts and bolts of what resources are available and how we'll extract them, I wanted to talk a little bit about, you know, why would we want to do this in the first place? What's the motivation for using space resources? And I'm going to kind of ignore the kind of ethical or moral questions of, you know, should we do this? Although that's a valid question to ask. So I'm going to kind of just assume that it's the goal of society or some subset of society to expand civilization out into space, okay? Now, to some extent, we're already doing that. We have the International Space Station in low Earth orbit, and then we had these brief forays to the moon and back in the 60s. But we're now living in a time where there are nation states and increasingly private companies like SpaceX, Blue Origin, who have credible plans to go further out into space and to stay permanently, okay? So if that's your goal, if your goal is to go out and set up a permanent settlement on the moon or on Mars, then you're really almost forced to use local resources, just from a logistical and an economic standpoint, okay? So why is that? Well, as an analogy, imagine you're back in 15th century Europe and your goal is to send settlers over and set up a permanent village or settlement in the New World, okay? And so here's your ships, and these are kind of replicas here, but you're going to load these up, and the first thing you have to take is all of the people who are actually going to be the settlers. And then you have to take all of the stuff, the food, the water, to keep them alive, or try and keep them alive on the journey over, okay? But your goal eventually is to create kind of a self-sustaining settlement in the New World, okay? So imagine, if you will, if you had to take all of the stuff that you would need once you got there on these boats, right? All of the wood to build your structures, all of the fabrics, all of the food, all of the water that you would need once you got there, okay? That would be basically impossible, right? You just don't have enough mass and don't have enough volume on these ships to take everything that you need once you get there, right? It doesn't make sense to take the wood that you're going to need. You would take a saw and cut down the trees that are already there, okay? So we run into basically the same problem today, okay? So these are now our ships that we have available. And again, the goal is to set up a permanent base on the moon or on Mars. And the problem is that there's just not enough mass and volume capacity to take everything with you from the Earth to set up that base, right? And that forces you to use space resources that are already there. So if we look at this, these are kind of the rockets that are flying today. This is the current generation. And to launch one of these, it costs about on the order of $100 million, okay, for a single launch. And if we look at how much mass these rockets can launch just into low Earth orbit. Okay, so not getting it to Mars, not getting it to the moon, just getting it off the ground. We're talking about kind of 10 tons, right? 10 metric tons. So $100 million to launch 10,000 kilograms gives you a launch cost of about $10,000 per kilogram. Okay, so that's basically like this much water. It costs $10,000 to launch into space. Right? So it really just doesn't make any sense to bring everything that you're going to need with you as you go out to the moon or out to Mars to set up a base. Right. Now, this is kind of the current generation of rockets. So what about the rockets that are coming down the line? You may have heard of things like the BFR from SpaceX. So this is kind of the next generation here. We have the Falcon Heavy, which has already flown, and the Vulcan from ULA. And these are kind of similar launch costs, right? So about $100 million. But now we're talking about a little bit more capacity, kind of 20, 30 tons into low Earth orbit. That brings down the costs a little bit, but that still doesn't really change the equation, okay? Now we have the New Glenn. This is from Blue Origin, and this is kind of secretive, so there's not really good numbers on this. And then the SLS that NASA is building is going to cost $1.5 billion every time it launches, if it ever launches, okay? So really what we want to look at here, though, is this BFR from SpaceX, okay? Now, this is not just a concept. They have already started building this at a facility in California. And they're projecting that it will be able to bring 150 tons into low Earth orbit. And because this is a fully reusable system, the projected launch cost is all the way down at $8 million per launch, right? Now, that might be a little bit optimistic, but even in that neighborhood, you're already talking about something like $50 per kilogram to launch stuff into space. So the question is then, does this BFR rocket, does it make space resources obsolete? If you would just bring everything with you for cheap, is there any reason to actually extract and mine and use resources in space? And I think there are kind of a few compelling reasons other than just this mass and volume problem, okay? So the first reason is that, if your goal is to not just have an outpost, not just have a short-term mission, but to actually stay and have a self-sustaining settlement on Mars, for example, then by definition, if this is self-sustaining, it's not relying on resupply or resources from the Earth, okay? You would be getting everything you need from the Martian environment, right? So that, again, forces you to use what resources are available on Mars. The other reason is that resources on Earth are finite, okay? And there's this relationship between, if we think of something like precious metals, okay, like platinum or gold, there's a relationship between the grade of the ore, so how rich the ore is, and how much energy or money it costs to extract that resource from the ground, okay? So as the grade goes down, as we use up all of the good stuff and we're left with depleted ores, the cost to extract new material goes up exponentially, all right? So for something like gold or platinum, as civilization continues to expand, population grows, technology increases, if we can't find a replacement for these materials and we can't recycle them efficiently enough, then eventually we're going to deplete the ores enough, and there will be a crossover point where it's so expensive to keep extracting those resources on Earth that it actually makes economic sense to go out into space and mine those resources in space. Okay, and then a third kind of reason you might want to use space resources is that eventually in the future, as civilization continues to expand and people are working and living in space, we may decide that just from an ethical standpoint, it might make sense to move all of the heavy industry on Earth off planet into space, okay? So instead of continuing to, extract resources and pollute the environment, you may decide that, let's move all of the heavy industry into space and keep Earth as a nature preserve. All right, so there are kind of a lot of compelling reasons, either from a logistical or economic standpoint or from an ethical standpoint, why we might want to use the resources that are available in space. So now I'm going to get into kind of the nuts and bolts of what resources are actually available and how we might go about extracting them. And to start with, I want to kind of dispel this myth, okay? So oftentimes when you hear about things like asteroid mining, you may have read news articles that say, you know, astronomers have found this asteroid with some billions and numbers of tons of platinum, and it's worth trillions of dollars, okay? First of all, there is no such thing as a platinum asteroid, okay? It's geologically impossible to have an asteroid made entirely of platinum, all right? And even if there were, if you think about it, you know, why are things valuable, right? It's either because they're useful or because they're rare, stuff like diamonds, or both, right? Stuff like platinum, gold, okay? So if there was a pure platinum asteroid out in the solar system and you went out and threw a lasso around it and brought it back to the Earth, then guess what? Platinum is no longer rare, right? So you've just crashed the market for platinum, right? So when we're talking about space resources and asteroid mining, it's really not about going out and extracting these precious metals and bringing them back to the Earth to get rich. What it really is using resources that are in place to support a space-based economy, right? And to enable space exploration and expanding out into space. So what I'm going to do is talk about what resources are actually available. And I'm going to use as an analogy this kind of three-age system that's used to divide up human history, okay? So you've probably heard about these. We have the Stone Age, the Bronze Age, and the Iron Age, okay? And these are really, there's three different materials, but what this really represents is a progression in how much processing and energy and technology is put into turning the stuff that's around us into something useful, right? So if we start with the Stone Age, this is really just, you know, walking around, you find a rock, you pick it up, and you smash something with it, okay? And if you're really creative, you could smash two rocks together and start to chip away at one and shape it into something like a spearhead, okay? But really kind of minimal processing, there's not a lot of technology or energy involved. You're just kind of using what's available, okay? Then when we go on to the Bronze Age, in this case, you're taking two metals, copper and tin, which may not be located in the same place. And then you have to develop the technology to create a forge to melt them and alloy them together and cast them into something useful, okay? So a lot more processing, a lot more energy and technology involved to actually turn the stuff around you into a useful resource. All right, and then finally, the Iron Age. Iron is a lot more difficult to work with than bronze. Okay, it has a much higher melting temperature, so you have to develop better furnace technology to get those temperatures to be able to actually work with iron and make more advanced tools. Okay. Now, of course, this is not, you know, it's not as clean and simple as this. There's not like a nice dividing line between these different ages, but it's just kind of a way of organizing human history. So what I've done is I've kind of taken this concept and mapped it onto space resources to show what types of resources are actually available and what's kind of a logical sequence for how we'll actually use them. Okay, so we have the regolith age, and regolith is just it's a technical term for dirt on another planet. Okay, that's the word that's used. So we have the regolith age, the oxygen age, and then the unobtainium age. And so what I'll do is just kind of briefly walk through each of these and show you what resources are actually available in space and how we might go about using them. Okay, so the regolith age, this is going to be kind of the first forays into using space resources. So optimistically, we're talking about kind of 5 to 10 years for the beginning of this. And the scale here is kind of at the scale of, you know, a large rover or individual astronauts in suits kind of walking around. Now, the basic idea here is that it's similar to the Stone Age. You're just using what's immediately available around you. If you go to the moon, go out to an asteroid, go to Mars, the most abundant resource is just the dirt, right? The unconsolidated rocks and soils that cover those planetary bodies, all right? So the first thing that you can kind of do is just simply move that material around or compact it and shape it into useful objects. Now, let's just say that you want to set up a base on the moon, okay? So the first thing you'd actually want to do is to have your habitat and bury it in a layer of regolith, about 1 meter to 2 thick. And the reason you do that is as radiation shielding. Okay? So the surfaces of the moon, the asteroids, Mars, they're not protected by a magnetic field or a thick atmosphere. Okay? So there are micrometeorite impacts, there's solar energetic particles, and then galactic cosmic rays. And if you're planning on spending any amount of time in those environments, you need to protect yourself from that radiation environment. Okay? And the easiest way to do that is to just put a lot of mass between you and outer space. Okay? And the easiest, really the simplest way to do that is to just take the soil, the dirt that's around you, and cover your habitat with it to shield yourself. The other thing that you want to do is actually build a landing pad. Okay, so why would you want to do that? If you think about it, if you're landing a spacecraft on the surface of the moon and it's coming down, you're firing rockets downwards at the surface, right, to slow your descent. The exhaust from those rockets is coming out at something like 3,000 meters per second. Okay? So as it comes down, that rocket exhaust starts to impinge on the surface of the moon or Mars. And what's going to happen is that all of the loose rocks and dirt that are on the surface are going to get picked up and ejected at huge velocities in all directions. Okay? So the first time you land something, you're fine because there's just nothing around you, right? But if you set up your base, your habitat, and then you want to resupply it, you want to have more ships come to that little habitat, then you have all of this infrastructure in place. And if you try and land a rocket right beside that, you're going to completely destroy all of your infrastructure. Okay? So the first thing you want to do, cover your habitat with a few meters of regolith, and then you want to construct landing pads and roads out of the regolith. A couple other things that you can do very simply with minimal processing is extracting water. So if you're on the moon, there are ice deposits in the permanently shadowed craters at the poles. If you're on Mars or an asteroid, there are hydrated minerals, things like salts and clays that actually have water in their structure. And so you could bake out that water. And that's fairly easy to do, just to turn ice into liquid water. Another thing that you can do with minimal processing, with just the regolith, is to try and grow plants in it, right? Obviously, if you want to have a sustaining settlement, you need to have a food supply. And so a lot of people are looking into how you could actually use native soils to grow plants. And I'll talk more about that later. So the basic idea here is that these first steps of using space resources, you're not going to be putting a lot of processing or energy into this. You're just kind of using what's abundantly available around you, and in this case, it's dirt on these other planets. Okay, so the next steps is what I'm kind of calling the oxygen age. And the idea here is that you're putting a lot more energy into breaking down molecules in the atmosphere or in the rocks themselves to get useful stuff out of these materials, right? And one of the most useful things is actually oxygen, right? Obviously, you can use it to breathe, but liquid oxygen is one of the best rocket propellants there is, right? So if you create propellant depots in space or on the surface of the moon or Mars, then what you kind of do is enable a transportation network in the same way that gas stations, enable you to have a highway system, right? Now, if you're on Mars, you can actually get oxygen directly out of the CO2 atmosphere. And on the next Mars rover, the 2020 rover, it will have a small little instrument that will do a technology demonstration to actually demonstrate this process. You can take water, of course, and split it into hydrogen and oxygen. Both of those can be used as rocket fuel. And if you're on the moon, what you can do is you can heat up the oxide and silicate minerals that are in the rocks and the soil and chemically reduce them to form metals as well as free oxygen. Okay. Now, the other thing that you can do if you're melting rocks is you can actually create useful fabrics and building materials. And this is actually something that's done on Earth. If you take, for example, basaltic rocks and melt them, you can spin them into fibers. And so you can make fabrics, you can make stuff that's kind of like rebar to use as a building material. And so if you guys want to come up after the talk, you can look at these materials. Okay, so the kind of idea here is that now we're entering this stage where you're really putting a lot more energy and technology and processing to turn the stuff that's in space, the rocks, the atmosphere, into useful consumables and construction materials. Okay, and then finally, the last is this unobtainium age. This is kind of the futuristic sci-fi type thinking, where now we have a huge scale. So we're talking about large factories either on the surface of the moon or Mars or free floating in space. Where you're putting enough energy in that you could extract and refine any element you want, things like platinum group elements, etc. You're talking about things like uranium ores or helium-3 on the moon to drive fusion or fission reactors. And then you could think about things like advanced ceramics, polymers, composites, and the possibility to create materials that don't exist on Earth. So you could take advantage of the lower gravity in space. You could take advantage of the lack of an atmosphere to think of things that aren't possible to synthesize on Earth. Okay, so again, I think this is not, there's not going to be nice, clean boundaries between these, but I think this is just a nice way to kind of organize and think about what resources are available and what's kind of a logical sequence or set of steps that we could take to actually exploit those resources. So what I'm going to talk about for the rest of the talk is this regolith age, these first steps, and the projects that we're doing at UCF to try and start to enable some of these technologies. Okay, so first I want to say a little bit more about the nature of regolith and what it's like. Right. On the left here, this is just a typical soil on Earth, right? And on the right, this is the regolith that the Apollo astronauts encountered on the surface of the moon. And these two things are really fundamentally different materials, okay? Dirt on Earth is, it's almost saturated with water. It's full of organic matter, so humic matter, bacteria, fungi, earthworms. It's in equilibrium with the atmosphere, which is full of oxygen, so all of the iron is in a very oxidized form. And it's this kind of heavily processed kind of living matter that's been evolving for millions of years on Earth. Regolith, on the other hand, is quite different. Okay, it exists in this kind of exotic environment, and it is an exotic material. Right. So if we take regolith on the moon, for example, it's almost completely dry. There's no organic matter whatsoever, and at the surface, it kind of has the consistency of bread flour. It's this very fine pulverized rock, right? The other interesting thing on the moon is that because you don't have any protection from the space environment, you get micrometeorites that come down and hit the surface, and they cause these little glassy particles called agglutinates to form. So you find these things all over the moon. They're very sharp and angular, and so that's why you can see that this regolith holds totally vertical edges. You can actually undercut it and it won't collapse. And you can see this stuff, it gets charged and it's stuck to all the equipment and all of the suits of the astronauts. So just a very different material, the regolith that you find on the moon, on Mars, on asteroids, compared to typical soils that we deal with on Earth. So one of the things that we've been doing at UCF is a project to try and recreate the properties of regolith in the lab to create synthetic space dirt, basically. And this project started a few years ago. This was during the previous administration when there was a planned NASA mission called the Asteroid Redirect Mission. Okay? So the goal was to go out to a near-Earth asteroid and either capture the asteroid, a small asteroid, or just pluck a boulder off of the surface of a larger asteroid. And then bring it back, put it in orbit around Earth or around the moon, and send astronauts up, and they could work with this asteroid, sample it, study it, etc. And so NASA was really interested in what the surface properties of these asteroids were like, particularly a type of asteroid called carbonaceous asteroids that are very dark, very rich in hydrated minerals and simple organic molecules. Right? We had meteorites in the meteorite collection that are believed to come from these types of asteroids, but there wasn't a lot of information about what the actual soils and surface properties are like. So NASA funded a joint study between UCF and a company called Deep Space Industries, which at the time was focused on asteroid mining. And the goal of the project was to develop synthetic asteroid material that we could use and study in the lab. And the way this worked was that UCF, we did kind of the prototyping, the scientific work to develop the simulated asteroid material. And then Deep Space Industries, DSI, they're based in California, but they set up a warehouse facility in Orlando where they were mass producing this stuff. So they were making metric tons of this fake asteroid dirt and delivering it to NASA and to other private research universities. All right, so the grants ran out in June of this year, and DSI decided that they didn't want to do this anymore. They wanted to focus on kind of their core business, which is now making thrusters that run on water and making spacecraft that can operate in deep space. So they pulled out of this and they donated all of the leftover equipment and materials from the project to UCF. So in June of this year, I kind of took over this project, and we've now rebranded this as the Exolith Lab. Okay? So the goal of this project is to create synthetic regolith for asteroids and other planetary bodies, to produce that material in kind of bulk industrial scale quantities, and then to distribute it to space agencies, to private researchers, and to private companies that are kind of trying to develop the technologies needed to extract and use space resources. And what we've done is we've kind of essentially set this up as a nonprofit, but instead of a kind of standalone company, it's running within UCF itself. But we're basically running this as kind of a nonprofit company. Okay. So we have a warehouse facility rented. We just took possession of it in the beginning of this month. This is us moving all of our hundreds of buckets of raw minerals and all of our equipment in here. And then currently, we're almost set up, so all of our raw materials here, we're setting up all our heavy equipment here, and in the next couple of weeks, we're planning on moving in and actually starting the large-scale operations. And in the meantime, we've been running everything else out of a small lab in a building at UCF. Okay, so in addition to the asteroid simulants, since starting this project, I've also developed new simulants for Mars and for the Moon. Okay, so what I thought I'd do is kind of walk through the process of putting together one of these simulants and how we actually do this. So we had this paper come out just a few months ago, kind of explaining the philosophy and the methods behind how you create, a simulant of Mars soil. So this Mars project started last year. We were approached by a group at NASA Kennedy, and these are the people who do the veggie experiment on the International Space Station. And this is where the astronauts are actually growing their own lettuce and other plants, and then they're actually able to eat those, which is kind of a nice break from the regular dehydrated food that they have to eat. So these guys at Kennedy are trying to figure out, looking ahead to future missions to Mars or the Moon, trying to figure out how you would actually go about growing plants on those bodies. And there were a couple of other Mars simulants that had been made in the past, but for the most part, those were just terrestrial soils that happened to be kind of orange in color. People said, oh, that looks like Mars. What these guys wanted was something better than that, because it's not that hard to grow plants in a soil that comes from the Earth. But when you go to Mars, you're dealing with a fundamentally different material. And so they wanted to replicate that as closely as possible. So the way we did this is we took a lot of our data from the Curiosity rover. So this is the latest rover. It landed on Mars in 2012, and it's been exploring Gale Crater ever since then. So here it is here, and it's kind of scooping into the dirt here. Now, Mars is covered with this kind of layer of dust, and it's called the red planet, but it's not like fire truck red, right? It's kind of this burnt orange brown color. And once you scoop beneath the dust, this is what the actual soil itself looks like, and it's kind of basaltic in composition. So the rover can scoop into the soil, it can take samples, and then it can deliver those samples onto scientific instruments that are inside the body of the rover itself. One of those instruments is something called an X-ray diffractometer. So it basically shines X-rays through the soil, and then based on how those X-rays diffract, you can kind of back out what the mineral composition of the soil actually is. Okay, so from that data, what we did was we developed basically a recipe for what soil on Mars is made out of. Okay, so these are all of the different mineral and chemical components, and then this is just the weight fraction in the soil on Mars. And at this point, it's kind of like baking a cake or something. You start with your recipe, and then you go out and source and find all of these ingredients, and then you mix them together to create your final Mars soil. This is actually the most challenging part of this project, is actually finding all of these minerals and being able to get them commercially. So in some cases, we get lucky because some of these things are actually sold on the open market as useful products. So for example, magnesium sulfate, one of the forms of that is the mineral epsomite. That's basically Epsom salts. So you can just buy that at CVS. You can buy huge pallets of it, no problem. There's other things that are kind of sold under more obscure trade names. So there's this mineral ferrihydrite. This is an iron oxide hydroxide, and that's responsible for a lot of the color on Mars. And it turns out that this thing is sold by pet stores under the name granular ferric oxide, and it's used to remove phosphorus from fish tanks. So you would never really know that because they don't use the scientific names, so it takes kind of a lot of detective work to find some of these products. Some of the other things, though, are a lot more difficult to find because even though they're common, they might be common on Earth, they're not useful, and so no one actually goes out and mines concentrated deposits of them. So last month, we actually took a trip out to Montana. This is the Stillwater complex. And there's a mine here, the Stillwater mine, where they're mining platinum group metals underground. But the Stillwater complex it's something called a layered igneous intrusion. And so you get this really nice separation between different minerals in this kind of volcanic deposit. And so we went out here and we collected more than 4,000 pounds of rocks and shipped them back to our warehouse facility. So what we do then, once we have all of our raw ingredients, we have to kind of mill them and process them. So this is our rock crusher here. We also have a bunch of ball mills, jaw crushers, sledgehammers. So we take all of our raw ingredients and mill them down and process them, and then we mix them together. So we have cement mixers, these commercial stand mixers. So we take all those things, homogenize them together, and then we can adjust the particle size distribution and try and get as close to Mars as is reasonably possible. So this is our final material. This is our Mars simulant on the right here, and then comparing that to the actual soil deposits that were investigated by the Curiosity rover. Now, you can never really make a perfect simulant, right? You're always trying to get as close as you can as is possible, but it's never going to be perfect. So a lot of what we do then is kind of analysis to look at how close we've come and what are the actual properties of these regolith simulants. So we can do things like heat up the sample. So this is showing heating the sample up to 1,000 degrees and looking at all of the gases that are coming off of it. So we can see water and CO2 and other things being evolved. And it turns out that the actual soil on Mars has about 1 to 2 weight % water. So if you wanted to, you don't have to go to the ice caps, you don't have to find these hydrated minerals. You could just process a huge amount of bulk soil on Mars and bake the water out of it to get your water that way. And then we've also looked at things like the spectral properties, so the color, the reflectance of these simulants, comparing them to actual data from rovers and from orbiting spacecraft on Mars. And the basic takeaway is that we've done a much better job in capturing the actual properties of Mars soil compared to some of these previous simulants. Okay, so with this exolith project, we've developed new simulants, we're producing them, and we're distributing them. And what we're also trying to do is work with different partners on kind of fundamental science projects and trying to mature some of the technology to make space resources a viable thing in the future. So I just thought I'd highlight a couple of those. The first one is working with this company called Transastra. This is an asteroid mining company based in California that's run by a guy named Joel Sercel. And what they've been doing lately is a lot of work focused on optical mining technology. The idea here is that if you want to extract water from an asteroid or from ice deposits on the moon, instead of using a lot of heavy digging equipment, a lot of moving parts, their idea is to basically blast the material with electromagnetic radiation. So either visible light, infrared, microwaves, and to get the water out that way and then trap it in cold traps. So this right here on the right, this is the most powerful light bulb you can buy commercially. It's a 32 kilowatt xenon arc lamp, and it costs $8,000 per bulb. And then there's this parabolic reflector right here. So they're setting up this test bed at the Colorado School of Mines, trying to develop this technology using our regolith simulants to develop this technology to be able to extract water from asteroid material or from lunar or Martian permafrost. And this is a picture here of one of these tests. So this is some of our asteroid simulant, and this is concentrated sunlight that's basically ablating away the surface and removing the water that way. Okay, and then the other project, this is something I already alluded to, this is looking at plant growth for Martian applications. So we're working with folks at NASA Kennedy as well as at Florida Tech to try and explore how you would actually go about growing plants on Mars. And it turns out that if you just take our regolith simulant, just fresh out of the bag, and try and grow plants in it, they all die almost immediately. Okay, and presumably that would also be the case on Mars. Right? So some of the things that we're exploring are, first of all, does it even make sense to try and use native soil to grow plants? Could you just use a hydroponic system instead? And if you do use the soil, are there harmful chemicals on Mars that you would have to take out of the soil? And what kind of fertilizer, what kind of processing would you have to do to get something that plants will actually grow in? So that's kind of an ongoing research project. Okay, so to date, we're kind of just getting started with this project. To date, we've already shipped almost 150 kilograms of these simulants, basically worldwide, to companies like SpaceX, groups including the European Space Agency and NASA. And then we have, on order, almost 700 kilograms that we have to produce. So I think this is kind of an exciting project to not only look at the kind of the fundamental science and engineering properties of this regolith, but then to kind of enable a lot of these technologies to actually start using space resources. So to take a lot of the stuff that I talked about in the first part of the talk and turn it from science fiction into actual reality. So if you want to kind of follow along, this is my personal Twitter account, and then we have a separate one that we're running for this project. So with that, I will thank you, and I'd be happy to take any questions.
Is there any research being put into, say, plant genetics to see if there may be a certain gene that can adapt to some of the elements inside of the simulated Mars dirt?
Yeah, I don't think we've worked with anyone on that yet, but I know there are people working on that. So, I mean, obviously, if you look at all the plants on Earth, some of them are a lot hardier than others. Some of them, have evolved to grow in low moisture contents. You think of things like lichen, and then the other thing is that you could do is so you could either, isolate those genes that allow those plants to do that, or you could, in theory, genetically modify plants to be able to grow under Mars conditions. So we haven't been involved with that research directly, but I think there are people working on that. Yeah. Yeah.
If you were to grow plants on Mars hydroponically, is there already the necessary nutrients to make like a hydroponic fertilizer on Mars?
Not directly. I mean, the actual elements themselves, like the nitrogen, whatever, are there, but not in a form that you could extract and create a nutrient solution. So that's something where you would be bringing the nutrient solution with you. Now you could think about obviously in a hydroponic system you have like trays, right? So you could think about, well, could you take the regolith and kind of form it into those trays to reduce the amount of mass you have to bring? But for the nutrient solution itself, that's something that for now you'd have to bring with you.
Is the regolith, excuse me, the regolith consistency the same across the whole planet, or in some part of Mars it's completely different than another? Like, do they know whether that's?
Yeah, I mean, it certainly varies. So there are regions where you would just expect to have like bare volcanic rock, right, and not much regolith. In other places, it's much deeper. In some places, you get sand dunes, so you get kind of sorting, and so you would isolate, just the sand size fraction. So there is a lot of variation, but for the most part, the entire planet is kind of covered with some amount of unconsolidated, crushed up rocks.
With those same percentages of like that recipe of?
Yeah, so that's a good point. So you could say, well, the Curiosity rover, that's just one spot on the planet, right? How do we know that that the soil's the same elsewhere? And so there've been about 5 landers or rovers that have successfully landed on Mars, and particularly the previous generation, so the Spirit and Opportunity rovers that landed in 2004. They didn't have instruments to measure the mineralogy, but they had instruments to measure the bulk chemistry, so the elemental chemistry. And those results were very similar at the Curiosity, Opportunity, and the Spirit landing sites. So you now have kind of 3 data points that are all showing you kind of a consistent soil composition. So you would expect that there could be some regional differences, but for the most part, we kind of think there is this kind of global basaltic soil that's more or less the same. Yeah. Mm-hmm.
How would you go about extracting water from the soil? Would you build a fire and try to boil it out?
So, I mean, you could do things. The basic thing you need to do is kind of put it in some container, heat it up, and then extract the water. So you could think of something really simple like a solar oven. So you just you concentrate sunlight on the soil, and then you have some kind of cold trap or some kind of distillation system. But basically, you just need to heat it up, get the water to come out of the soil, and then you need some way to recondense it into liquid water.
How deep were the soil samples from Mars? Was it just surface, or did they actually do a proper soil sample tubing down?
Yeah, so for the Curiosity rover, it's just surface, so it has like a scoop. So you're kind of talking like centimeters deep. The European Space Agency is launching something called the ExoMars rover in 2020, and that will actually have a 2-meter drill that will be able to drill down into the surface. But to do like kind of proper soil sampling and like coring, that's kind of you're talking about humans being there to actually do a full kind of campaign and sample things properly. Yes?
Yes, you made a comment about moving heavy equipment to the Earth,
Mm-hmm.
excuse me, to the Moon,
Mm-hmm.
so that we can protect the Earth.
Mm-hmm.
So my question is, are there people out there running scenarios that if we put these bigger pieces of equipment or even a small factory out there, that it might affect the orbit of the Moon or the 28-day cycle or even our tides?
So I think even if you think of like massive factories, there's still many orders of magnitude less massive than the Moon. So you would really have to put a lot of material up into the kind of the Earth-Moon system to start affecting things. Yeah, if you think of all the satellites that are in orbit currently, communication satellites, the mass is just so insignificant compared to something like the Moon. So I think that's kind of really, really far in the future when you would actually get up to those kinds of scales.
Or even if you use the construction of whatever it is you're using,
Mm-hmm.
I mean, what if it has some sort of magnetic quality that it becomes more of a target for meteorites, et cetera? I mean, in everything affects everything on the Earth. You're saying you're gonna move this now to the moon.
Yeah.
So I'm just asking, how does that affect us back on the Earth?
Right, so I mean, everything has an effect, right? Every object with mass has, gravitational effects and affects everything else. It's really just a question of the scale, right? So, I mean, there's gravity attracting everyone in this room to each other, but you don't feel it because the scales are so small. So in terms of putting things in space and affecting the gravity, the magnetics, you really have to talk about enormous scales before you would actually notice those effects. Those effects are there, but it's such a small scale that it's hard to have an effect, a noticeable effect.
Are any of the companies that you're working with providing co-op opportunities for students?
I think so, yes. I mean, NASA has internships, summer internships. I think companies like ULA, Boeing, they all run internships. A lot of that is more focused on the engineering side. So a lot of these companies, these are aerospace companies. Their main business is in building and launching rockets. And this kind of stuff, the space resources, is kind of a side project for them. So there might not be opportunities right now to directly work on this stuff, but a lot of those companies do have student internships available.
Yeah. So how about moon regolith?
Yeah.
How does that fare as agricultural material?
Yeah, I think it's going to be, my sense is that it's not going to be very good to grow plants in, especially just because of the consistency. It's very fine. So if you're thinking about soils on Earth, you have kind of you have some combination of sand-sized materials, silts, and clay. And for growing plants on Earth, you want something that's called a loam, which is kind of a sub-equal mixture of those three. So on the moon, you have this kind of bread flour consistency, and that's really going to affect how permeable the soil is and how much water is retained in it. So my sense is that that's not going to be very good. Now, of course, you could take a sieve, right, and just sift the soil, sort out the particle sizes that you want. So I don't know that the lunar soil would be directly harmful to plants, but it might not be beneficial. It might just serve as kind of a bulk matrix that you add your fertilizer and then you have material to grow plants in. Yeah.
You said that Exolith delivered 144 kilograms of the recipe there?
Yeah.
Do you have access to any of the data from the research from that?
So from the people who are using it? Yeah, so it kind of varies. Some people were just happy to kind of ship them simulant and they can kind of do whatever they want with it. We'd always appreciate to hear about the results of their project or whatever. And then some cases, like the projects that are highlighted, we're actually in direct communication and collaborating with these people on the research. So in that case, we are privy to the results of the analysis. Yes?
How are you going to convert the carbon dioxide out of there's no air on the moon?
Right.
And so then photosynthesis is carbon dioxide converted to sugars,
Right.
but there's no carbon dioxide up there.
Right. So that stuff is kind of more thinking about Mars. For the moon, obviously, if you want to have plants, you would have to put them in a contained, pressurized environment. So if you want to have a gas, if you want to have CO2 or other gases, you would probably have to bring those with you for the moon. And if you have a base with astronauts, you're going to have a pressurized, kind of stable environment anyways. And so as some extension of that, you might have a greenhouse that's also pressurized. Yep.
How did your Mars soil retrolith stand to microorganisms like fungus or bacteria?
Yeah, so we haven't done any experiments ourselves to look at that, but I think there are people actually using our simulants to work on that. If you kind of think of it, if you think of these volcanic islands that form out in the ocean, and you just have fresh rock, right? what kind of happens is you go through this succession sequence where that rock is eroded, and then bacteria are introduced, they get into the soil, and then you have earthworms, and so there's this whole kind of sequence that takes place. And so there is a lot of interest in what kind of microbiome do you need in the soil to support plant growth, how much actual processing by things like earthworms needs to take place. So there are people working on that. I don't have any useful data right now. So. Yeah.
So you say you guys don't do any research on the regolith that you guys produce, or not that much as compared to the field that you sell with. So since you guys are a nonprofit, do you guys think that you will be using some of the proceeds to fund projects within the agreement to do further research on the regolith?
Yeah, that's one of the ideas. We're kind of just getting started right now, so for now we're just trying to kind of recoup our costs of the raw materials, the facilities, et cetera. But there is the opportunity for us to, and we do have plans to do a lot more fundamental research on the properties of regolith itself, particularly looking at things like construction, so like 3D printing with regolith, making kind of composite materials. So I think there is a lot of opportunity for us to, as we continue to work with this stuff and make it, to also have our own research projects ongoing.